This is Calculus 1, Lecture 4. This is going to be a quick one. We're just going to talk about the derivative at a point. So first of all, what is a derivative? Derivative is just a precise way of talking about change. It tells us how one quantity changes as another changes. On a graph, the derivative is going to be the slope of the tangent line to a curve at a single point. Derivatives can also be thought of as instantaneous rates of change. So recall, we talked about average velocity and instantaneous velocity. And if we were to look at plots of these, the average velocity on, say, a position function was calculated using two different points in time. So at point A, time point A, you would look at where the function is, or where the object is. At time point A plus h, you would look at where the object has traveled to, and you would use essentially the slope, right? You would calculate the change between these 2 points, the change between these 2 points, and that would be your average velocity, the slope of this line. Okay. Now, if we wanted to do the instantaneous velocity, this is when that second point gets closer and closer and closer to the first point until it's actually entirely coinciding with the first point. And now this is the rate of change at a single instant of time. Okay, and for this part we needed calculus and limits for. Okay. So quick review, a secant line is cutting through 2 points in a curve. A tangent line is cutting through only a single point on the curve. And this is just a visual representation of what happens as h approaches 0 for these graphs. Okay, so as h approaches 0, a plus h is approaching a, and f of a plus h is approaching f of a. So this point is coming down the curve. It's getting closer and closer to your first point. And you can see as that happens, the slope of your secant line is changing. Okay, it's dropping. And it's going to continue dropping. Okay, so from the orange curve to the green curve. Right, now we're getting a more and more accurate estimation of the instantaneous rate of change at A. Okay, so the secant line, in other words, is approaching the tangent line until it actually just becomes a tangent line. So until your second point actually just coincides completely with your first point, and you no longer are looking at an average rate of change, you're looking at an instantaneous rate of change. So this is what's happening kind of visually as h approaches 0. These points are getting closer, and the slope of your secant line is becoming the slope of the tangent line. In fact, your secant line is becoming your tangent line. Okay? Now, if you remember, the slope of the secant line was given by your general slope formula. M is equal to y2 minus y1 over x2 minus x1. In the terms that we're using here, f of a plus h minus f of a for our y values. And then we have a plus h is our x2, and a is our x1. And this is going to simplify on the bottom to just h. Your a terms will cancel. Okay, so as h approaches 0, the secant line approaches the tangent line, and just like we said, naturally the slope of the secant line approaches the slope of the tangent line, assuming that that limit exists. Okay, so this brings us to a really important definition in calculus. This is known as the limit definition of the derivative. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a, all of it over h. Okay? So in calculus, we just refer to this in general as the derivative of f of x at x equals a. The derivative allows us to calculate the instantaneous rate of change of a function at a single point a. Okay? So some alternative notation you might see. So if y is equal to f of x, the derivative can be written as f prime of x. This is probably the most common notation. Sometimes you see y prime. Sometimes you see dy over dx, and this is telling you that you're taking the derivative of a function y with respect to x. This is much more useful in higher level calculus where you have a multivariable function. You can take that derivative with respect to different variables. It could be x or z or y or something like that. Okay, and if you notice, this is actually just coming from our slope formula, delta y over delta x. So this is now that delta is becoming dy and dx for that infinitesimal change. Okay, and you might see d of f of x over dx, the derivative of f at x. All right, let us look at an example. So let's suppose f of x is equal to 19x plus 12. We want to determine the instantaneous rate of change at x equals 8. Okay, so this is our a value over here. So we start off with our limit definition, and in place of a, we can just put in 8. So we have f prime of 8 is equal to the limit as h approaches 0 of f of 8 plus h minus f of 8 over h. We go ahead, we substitute both of these into our original function, where x is. So we get 19 times 8 plus h plus 12. And then for the second one, f of 8, we're just plugging in 8 into the function. Okay. You can go ahead and distribute this and this as well. We're going to get 152 plus 19h plus 12 minus 152 minus 12. Our like terms will cancel. We'll be left with 19h over h. H's cancel. And, well, your final answer isn't even dependent on h. So it doesn't matter that h is going to 0. Our final answer is just 19. And this is going to be the instantaneous rate of change at x equals 8. Okay, for our next example, we've got k of x is equal to negative x squared plus 6x plus 5. They're asking us to find the slope of the function at x equals 2. And by this, they mean find the slope of the tangent line to the function at x equals 2. And then find the equation of the actual tangent line at x equals 2. Okay, so let's start off with our limit definition of the derivative. We know that k prime of 2 is going to be equal to the limit as h approaches 0 of k of 2 plus h minus k of 2, all of it divided by h. We can just go ahead and we can directly plug in 2 for a. Okay. Then we're going to substitute each of these everywhere we see an x into the function. So in the first part, we've got negative parentheses 2 plus h squared plus 6 times the quantity of 2 plus h plus 5. And then minus, and in the second brackets, we plug in 2 everywhere we see an x. So negative 2 squared plus 6 times 2 plus 5. All of it divided by h. Go ahead and expand so we can use our FOIL, and then we can distribute that negative sign. So we're going to get negative 4 minus 4h minus h squared plus 12 plus 6h plus 5. This is going to be a negative 4 plus 12 plus 5, and then we're going to distribute that negative, and all those signs will flip. Okay. Next, we're going to combine like terms, and we see that all of our constants actually cancel out nicely. We're left with only h terms. So we have negative 4h minus h squared plus 6h, all of it divided by h. We go ahead and factor out an h from the top and divide that with the 1 on the bottom. We'll be left with the limit as h approaches 0 of negative 4 minus h plus 6. Go ahead and now use direct substitution, plug in 0 for h. And we're left with just negative 4 plus 6, which is equal to 2. So our slope of the tangent line here at x equals 2 is m equals 2. Okay, or k prime of 2 is also equal to 2. All right, so this is our slope. Now we have to use something like the point slope form to find the equation of the tangent line. Okay, so point slope form went with y minus y1 is equal to m times the quantity x minus x1. Okay, so x1 being the actual x coordinate of interest, y1 being the y coordinate of interest, and m being the slope that we actually just found. Okay, so we have our x1. This is just 2. This is what the problem gave us to begin with. They said find the equation of the tangent line at x equals 2. So this is our x value of interest. We just found m, which is equal to k prime of 2. And the last thing we need to find is the y value associated with our x1. For this, we go back to our original function k of x, right? So k of x is kind of just the same thing as y. Y is equal to k of x is equal to negative x squared plus 6x minus 5. Okay, plug in our x1 of interest, which is 2. The negative of 2 squared plus 6 times 2 minus 5. All of that is going to reduce to just y equals 3. Now let's go back to our point slope formula. We've got all of our components. X is equal to 2, y is equal to 3, and m is equal to 2. We substitute them in. y1 is 3, m is 2, x1 is 2. Go ahead and distribute and solve for y. You're going to get that y is equal to 2x minus 1. This is the equation of your tangent line when x is equal to 2. Okay? So those were just 2 quick examples. That's all for this one. If you found this lecture helpful, please give it a like and subscribe so you don't miss the next one. Thank you for watching.